Hey everyone, welcome. You ever stop to think about what it takes to get something perfectly still? In a world where everything is constantly being pushed and pulled? Well, today we're going to dive right into that. We're talking about the physics of perfect balance, but with a cool twist. We're going to use the invisible forces between electric charges to figure it out.
It's kind of like a game of tug-of-war, right? For that little flag in the middle to stay put, both teams have to be pulling with the exact same strength, but in opposite directions. So today, we're doing the same thing, but instead of teams and a rope, we're going to play with tiny electric charges and the invisible forces between them. Let's see if we can create that perfect, balanced standoff.
Okay, so to really get into this, we've got a little puzzle for us to solve. Think of it like a mystery. We've got this one electric charge, and it's in a bit of a jam. It's being pulled every which way. Our job? We got to figure out how to make it hold perfectly still. How do we get it into a state of perfect equilibrium?
All right, here's our whole setup. You can think of it as the scene of the crime. We've got three charges, and they're locked in place at the corners of a perfect equilateral triangle. The one at the top, at point A, that's our main character. Then you've got two others at points B and C. The big mission, should you choose to accept it, is to figure out what fourth charge we need to place right at point M to make our charge at A stop moving entirely.
Okay, every good detective needs the facts, right? So here's our case file. The charge at A, our charge in peril, is positive. Down at the bottom, the charges at B and C are both negative, and they're exactly the same. Oh, and you see that μc? That just stands for microcoulombs. A coulomb is the unit we use for electric charge, so a microcoulomb is just a teeny tiny fraction of that, 1/1,000,000th to be exact. So the goal is super clear. We need to make all the forces acting on charge A cancel out completely. Zero net force.
All right, we've got the facts. The investigation is officially underway. First things first, let's figure out what forces are already messing with our charge at A. So the one big rule that controls this whole puzzle is something called the electrostatic force. You might also know it as Coulomb's law. And honestly, the main idea is super simple. Opposites attract and likes repel. That's it. That simple rule is the only tool we need to understand what's happening to charge A, and it's exactly what's going to help us crack this case.
Okay, let's check out our first suspect, the charge down at point B. Now B is negative, and our charge up at A is positive. And what do opposites do? They attract. So charge B is pulling on charge A. It's an attractive force tugging A down and to the left, right along that line connecting them. All right, what about our second suspect, charge C? Well, it's also negative, just like B. So you guessed it, it's also pulling on our positive charge at A. This time, though, the pull is down and to the right, straight along the line between A and C.
So, let's recap. We've got two different forces pulling on charge A. But, and this is a huge clue, since the charges at B and C are identical, and since they're the exact same distance away from A, it is an equilateral triangle, that means the strength of their pull is exactly the same. They're pulling with equal force.
Okay, so we have two equal forces, pulling in two different directions. What's the net effect? When you add them up, where is charge A actually going?
Just think about it for a second. One pull is down and left, the other is down and right, with the same exact strength. So, where do you think it ends up going? What's the combined result? And here's the beautiful part. Because everything is so perfectly symmetrical, the left part of the pull from B gets completely canceled out by the right part of the pull from C. Sideways, they're in a total stalemate. They cancel each other out. But, and this is key, the downward parts of both forces, they team up. They add together, creating one big, strong pull straight down. So here's the verdict. The combined pull from B and C results in one single net force, and it's yanking charge A straight down, right towards the middle of the triangle's base. So our charge is definitely not balanced. It's actively being pulled away.
Okay, now we know the problem, right? There's a net force pulling our charge straight down. So now we can finally figure out the solution. It's time to bring in a new player, a hero if you will, to come in and save the day.
You know that old saying, for every action, there's an equal and opposite reaction? That's kind of what we need here. We have a downward action, so to cancel it out, we need an equal and opposite reaction, an upward force that perfectly matches the downward one.
And the puzzle tells us exactly where our hero needs to be, right there at point M, the midpoint of the base. Its mission is simple but crucial. It has to create an upward force with the exact same strength as that downward pull we just figured out.
So let's pause and think about this. Our charge up at A is positive. We need our new charge at M to create an upward force on A. An upward force would be a push, right? A repulsive force. So what kind of charge does our hero at M need to be? Well, remember the rule. Likes repel. To push a positive charge away, you need another positive charge. Simple as that.
We're so close. We figured out where our hero charge needs to go, point M. We know what kind of charge it is. It's positive. There's only one mystery left to solve. How strong does it need to be? What's its exact magnitude? All right, this is the final showdown, the math part. We'd use Coulomb's law to calculate the exact strength of that downward pull from charges B and C. Then we'd use the same law to figure out the upward push from our hero charge at M. And the final move, we set them equal to each other. Downward force equals upward force. That creates a perfectly balanced equation, and all we have to do is solve it to find the exact strength of our hero charge.
And when you run the numbers, here's what you get. The answer to our puzzle is a positive charge of about 3.9 microcoulombs. You place that charge right at point M, and its upward push will be the perfect match for the downward pull. A perfect cancellation. And just like that, mystery solved. With our hero charge in place, that plus 3.9 microcoulombs, the upward push and the downward pull are in a perfect standoff. The total force on charge A is now 0. It's in perfect equilibrium, held completely still in this invisible web of forces. So that about wraps it up for this one. But hey, before you go, here's something to chew on. What if that charge at A, our charge in peril, had been negative instead of positive? Suddenly, those negative charges at B and C would be pushing it away, right? Creating an upward force. So, how would our hero charge at M have to change to counteract that? Give it some thought. Thanks for tuning in.